Welcome to Drone Systems and Control course. In the last lecture, we talked about state space representation of any system. We discussed what is state space, what elements of physical systems are required, right? And then we talked about state space to transfer function, and we showed that for a multirotor system, taking in yard dynamics, we talked about how we can represent them in a state space form and how to get the transfer function from the state space form. Today we are going to talk about different forms of state space representation, that's canonical forms, very important concepts on state transition matrix, some understanding of system controllability and observability we are going to do in this lecture. So what's the objective of today's lecture? We're going to understand concept of state transition, right? Transformations, learning about canonical forms. Particularly we are going to focus on two: controllable canonical form, Jordan canonical form. In addition to that, we have observable canonical form, right? Understanding the concept of state transition matrix, right? How it will be useful. Understand controllability and observability of the system. This is very important to analyze the system in state space, and also useful for us to do controller design, understanding stability, detectability of a system. Okay. Let's consider general differential equations. d n y by dt n a n minus 1 d n minus 1 by dt n minus 1. I can represent in nth order differential equations, and you have this input term also, right? Now if I take a Laplace transform, again initial conditions we assume that to be 0. If we take a Laplace transform, then we will get Sn power ys a n minus 1 Sn n minus 1 ys all the way. Similarly, you will have b naught us to bn minus 1 us, right? We talked about this when we talk about a classical system, right? Then we can get a transfer function by taking ys term on the left hand side and us term on the right hand side. Ys by us is my transfer function, which can be represented in this form. You see, it's an nth order system. Okay, just for understanding and recap this again, right? Now when you have an nth order system, I can write this, because you have a numerator polynomial, I can write this y of s by u of s as y of s by x of s into x of s by u of s. I can rewrite, right? So y of s by x of s is nothing but the numerator term of the transfer function divided by 1, right? And then x of by u of s, I can write it 1 by s power n minus s power n a n minus 1 s power n minus 1 all the way to a naught, right? So y of s by x of s is this, then y of s is nothing but this particular term into x of s, right? Now I am taking an inverse transform. So if I am going to write y of t is b naught x of t, b1 x dot of t, that is dx of t by dt, bn minus 1 d power n minus 1 x of t by dt minus 1. Okay. Similarly, I can define x1 is x of t, x2 is dx by dt, that is x1 of t, xn, which is nothing but d power n minus 1 by dt, right? dt power n minus 1, I can define this is nothing but xn minus 1. If you see, x1 is x, x2 is dx by dt, which is nothing but x dot, right? That is nothing but x1 dot, right? The same way I can write for every states of the system here, right? So I can write this y of t, if I want to substitute this in this particular equation, then I can write y of t is b naught x1 of t, because x of t is nothing but x1, b1 dx by dt, the dx by dt is nothing but x2 of t, b1 x2 of t, bn minus 1 d power n minus 1 x of t by dt minus 1. That's nothing but xn. So I substitute this xn, right? I get the equation y of t in terms of x here, right? There are n states here. Now I'm going to consider the second part of the transfer function, which is x of by u of s. The x of s by u of s is nothing but 1 by s power n, a power n minus 1, s power n minus 1, all the way to a naught, right? So take them into denominator, shift to this left hand side, then x of s can be represented in terms of u of s, right? Again, taking the inverse Laplace transform, this results in d power n x of t, t power n, a n minus 1, d power n minus 1 x of t, dt n minus 1, all the way to a naught, and which is equal to u of t, right? I am trying to write this d power n x of t dt power n. I am just retaining that and moving all the rest of the terms in the left hand side of the equation to right hand side. Then it becomes negative a power n minus 1 d power n minus 1 x of t dt minus 1, all the way to minus a naught x of t plus u of t. We have already defined, right? x1 is nothing but x of t, x2 is x1 dot, we have defined, xn of t is xn minus 1 dot of t, that is derivative, right? We can substitute x1, x2, xn in this equation. If I substitute, x1 dot is x2, x2 dot is x3, x3 dot is x4, which we saw in the previous slide. Xn minus 1 dot will become xn. If I take xn dot, derivative of this, right, that is nothing but d power n x t power n, right, x of d power n of by dt power n x of t, which is xn dot, right? Xn dot is a naught x1, a1, x2, all the way to a n minus 1 xn plus u, right? I can substitute that, right? Now I have a relationship of first order differential equations for n states, right? If I'm just creating a state space form, this is nothing but controllable canonical form, right? x1 dot, x2 dot, x3 dot, all the way to xn dot. x1 dot is x2, that's why 0, 1, rest of the elements are, it's not depends on rest of the state. Similarly, xn minus 1 dot does not depends on n minus 1 state, it depends on nth state. Xn dot has all the terms of denominator coefficients a naught, a1, a2, an minus 1, and it depends on u. So I can represent them. This is a very special form. It's required for us to do a pole placement design. We'll talk about it when we go into controller design using state space. Okay. Y equal to b naught, b1, b2, bn minus 1, x1, state space vector x, and b naught u. This approach transform, this particular transform is called phase variable form, or it's called controllable canonical form. Let's take an example to understand how do we represent the multirotor system in a controllable canonical form. Let's consider a hover condition, right? We take a multirotor, we are trimming the aircraft at a hover condition. The equilibrium point is hover. What I meant equilibrium point is hover means the thrust produced by the multirotor should be equal to the weight. H should be constant, right? At a specific height I need to hover. I should not have any velocity. UVW should be equal to 0. I don't want the vehicle to move. I don't want the vehicle to have any pitch, roll, yaw, right? I don't want any of the rates to be present, right? Now I'm in that condition, I'm only looking at the pitch dynamics of it, right? That is theta dot will be q of t. In the modeling lecture, we derived the mathematical model which is of a nonlinear form. By substituting the Hoover condition, I can linearize the nonlinear equations into linear term, and that's what I am showing it here. The Q dot, that's a pitch rate, depends on MQQ of t plus M omega 1 C of t. Omega 1 C dot of t is TQ of t, T omega 1 C of t, and TV VD of t. This VD is a differential voltage, that's the input to the system. Right? Theta is a pitch angle, which is in radian. Q is pitch rate, radian per second. Omega 1 C is a differential rotor speed required to get the pitch motion, which is usually represented in RPM. VD is a differential motor voltage, which is an input, which is a control input for the pitch motion. Right? So, what are these terms MQ, M omega? MQ is pitch damping derivative, effect of pitch rate on pitch acceleration. M omega is a control effectiveness of omega 1 C on pitch acceleration. TQ is the effect of pitch rate on rotor speed dynamics. T omega is a rotor speed self dynamics coefficient. TV is the control effectiveness of voltage input on rotor speed. Okay. Now, I am trying to understand interpretation of these variables, what's going to happen in terms of how it's going to influence. MQ, if you look at, it has tendency to resist the pitch motion, which capture the aerodynamic damping. M omega, it is the effect of rotor speed on pitch acceleration. It captures how differential thrust influence the pitching moment. TQ, effect of pitch rate on rotor acceleration, usually small, may reflect gyroscopic or dynamic coupling which is present. T omega, which is nothing but a damping or inertia in rotor speed response, captures inertia or electronic / motor damping effects. Right? TV, it's most indicate how the differential voltage changes omega 1 C and depends on electronic speed controller gain and motor time constants. Now, if I take the dynamics of pitch dynamics at a Hoover condition, right, I can write them in a state space form, taking theta, Q and omega 1 C are the states of the system, right, and VD is your input. If I try to write it, you will get 0 1 0, 0 MQ M omega, 0 TQ T omega, X of t and VD. Okay. That's my state space representation of my pitch subsystem of multirotor. And what is the output I want? I want to get the theta, that is pitch attitude. So, my C is 1 0 0 X of t. Now, if I take a transfer function, we discussed about how to get the transfer function from state space form. If I get a transfer function, my the transfer function of a pitch subsystem will be M omega TV is a third order polynomial, S cube, MQT omega S square, M omega TQ minus MQT omega S, right. That's the third order polynomial is what we get, right. This is a transfer function for pitch subsystem. Basically, I am looking at theta of S by VD of S, right. I can write this in a general form, right. S cube plus A2 S square plus A1 S plus A naught. Remember, A naught is 0 here. The numerator polynomial, I can write it as a B2 S square plus B1 S plus B naught. Remember, B2 and B1 are 0. You get only B naught here. When you are comparing these two transfer functions, you can get the coefficients, right. B2 is 0, B1 is 0, B naught is nothing but M omega TV. A2, if you look at, that's nothing but minus MQ plus T omega. A1 is M omega TQ minus MQ T omega, and A naught is 0. We don't have any constant here, right. Now I want to write them in the controller canonical form. If I'm trying to write them in a controller canonical form, my states of the systems will be different. Xc dot of t is AC Xc of t plus BC U of t, y equal to CC Xc of t and DC U of t, right? So we saw how to write them in a controller canonical form. Once you have the transfer function, that's nothing but your denominator, and the coefficient of them will just come into this A matrix minus A0 minus A1 minus A2, which is nothing but the first column will be 0 because A0 is 0. The second column will have 1 0 m omega tq minus mq t omega. The third column will have 0 1 mq plus t omega. Okay. So your CC, right, will have B0, B1, B2. That's nothing but m omega TV 0 0, right? Your BC is 0 0 1, DC is 0. So I can represent the pitch subsystem in a controller canonical form, right? Now let's take another example. yaw subsystem. We've been discussing about yaw subsystem in the previous lecture also, where we talked about state space representation. So just to recall, yaw subsystem R of S by Vd of S, if you take, which will be a second order system, S square minus Nr plus T omega S, Nr T omega minus N omega Tr, right? And the numerator will have NVS plus N omega TV minus NV T omega, right? If I am going to compare with the general system, G of S will have S square A1 of S plus A0, B2 S square plus B1 S plus B0. So if I substitute, B2 is 0, B1 is 0.1, B0 is 0.301, right? A1 will be 15.55, A0 is 0.7755, right? So I get those coefficient. I can get B2 is 0, B1 is NV, which is 0.11, B0 is TV N omega minus NV T omega, which is 0.301. Your A1 is minus NR plus T omega, which is 15.55. Your A0 is NR plus T omega, which is 0.7755. So I can write directly the controller canonical form for yaw subsystem. Your A matrix will have 0 1 minus A0 A1, which is 0 1 minus 0.775 minus 15.55, because you see the denominator is positive. Okay. CC is B0, B1. Okay. Now general transfer function, if we take, these controller canonical forms are very useful when we talk about pole placement, the controller design. There is another interesting form of state space representation, which is a Jordan canonical form. In Jordan canonical form, if you want to get any state space representation, we can try to find out the eigenvalues of the state space, and using the eigenvalues, if the eigenvalues are distinct, then your Jordan canonical form has a very special representation. If it's repeated root, it has a different representation. More details of it, you can look into the reading materials. But I'm going to take one specific form, which is quite common in a multi-rotor system. I'm going to represent that particular form. One also need to recap on diagonalization. Any matrix given, they need to know how to transform that matrix into diagonal form, right? Which is covered in linear algebra course, right? But for this particular course, it's important to understand, if I have a distinct root, how am I going to represent, how am I going to use this canonical form for my design purposes. So any transfer function given to me, I'm going to write them into the poles. You see here the characteristic equation, usually it will be given in nth order polynomial. I am giving it in the product of the poles. So I try to do the eigenvalues, and all these P1, P2, Pn are those eigenvalues of the system. I am representing them in this form. right? If you see, all these poles are distinct, right? No repetitive poles. So we can use a partial fraction for this particular transfer function, and we can write it in this form: C1 by S plus P1, C2 plus S plus P2, and etc. Cn by S plus Pn, right? So in such case, we can say x1 of s is 1 by S plus P1 into U of s. If I'm taking x1 of s into S plus P1 equal to U of s, if I take an inverse Laplace transform, I get x1 dot minus P1 x1 equal to U. Similarly, I can write x2 of s is 1 by S plus P2 into U of s. I cross multiply and take an inverse transform. I inverse Laplace transform, you get x2 dot minus P2 x2 equal to U. Similarly, xn of s is 1 by S plus Pn into U of s. You cross multiply the term and take an inverse Laplace transform, you get xn dot minus Pn xn equal to U, right? Now, what is the diagonalization or diagonal representation of this? x1, x2, xn. You see, all the poles of this system will form the diagonal element of the A matrix, right? By looking at this representation, I can talk about whether system is stable or not. All these poles falls on the left half of the S plane, right? Then I can say this system is stable. Any of them is positive, then it means the system is unstable, right? So if you have 1, 0, then you know it's a marginally stable. If you have more than one pole located in imaginary axis, you can say that system is unstable. This form, we can just, by looking at the representation, we can comment about the stability of the system, right? And y will be C1, C2, Cn minus 1, and that's how you represent your Jordan canonical form if you have a distinct roots. Okay. Now we look at our yaw subsystem. We know our yaw subsystem is a second order system, right? I'm trying to represent the characteristic equations, right, in two poles. We know there are two poles. One is at minus 15.555, the other one is 0.05. If we have two poles, right? So I'm doing a partial fraction again. The g of s, I'm trying to represent 1 by 15.5 plus C1 by this, C2 by this. C1 is nothing but 0.0909, C2 is 0.0191. So I can represent them in a form like this, right? So we know now what is C1, what is C2. We know the pole locations. We can write directly in a Jordan canonical form. The A matrix will be minus 15.5 minus 0.05. Your B matrix will be 1, 1. C matrix is the coefficient of the partial fractions, C1 and C2, and D, right? So I can transform the yaw dynamics into Jordan canonical form, right? Now I'm going to present all the forms of yaw subsystem, right, so that we can appreciate R dot. If you look at, right, it's a general representation based on the linearization. I can represent them from the physics of the system and physical model and apply the Hoover condition, linearize. When I linearize, I get this form. I substitute the coefficients, I get R dot and omega d dot in this form. This is the standard representation of this state. I can represent them in controller canonical form, right? You have a controller canonical form representation, right? And if I'm going to do it in Jordan canonical form, you have this. All these three forms represent the same yaw subsystem. So what does it mean? State space representation is not unique. You can transform the state space representation from one form to another. You need to know how to do the transformation if somebody has given in this form to controllable form or Jordan canonical form, right? Okay. Now another important concept is solution to the state space equation. X dot of t is ax of t plus bu of t. Right? What does the general solution look like? If I am trying to get the solution, x of t is e power a t, right, into x of t naught. T naught is a initial time t t0 plus integral t0 to t e power a t minus tau b u tau d tau. That's my general solution for state space representation. Right? What is the state transition matrix? Phi of t, which is nothing but e power a t. Right? What is the significance of this state transmission matrix? I am not deriving the solution. You can look at general control textbook if you want to understand how we get the general solution, because that's beyond the scope of this particular course. That will be covered in more detail in control systems course. Right? What is the significance of this state transition matrix? It describes how the system going to evolve over a period of time. It allows the predictions of future states. It is useful in stability analysis. It's a key in controllability and observability test. Right? Now, how do we get this state transition matrix phi of t, which is nothing but e power a t, which can be computed Laplace inverse of Si minus a whole inverse. Right? If A matrix is known, I can compute Si minus a whole inverse and I can take the inverse Laplace transform to get my state transition matrix. Right? Now what are the properties of state transition matrix which will be really useful for me? Phi of 0, which is the identity matrix. Phi of t power n is nothing but phi nt. Phi of t, which is e power at, right? E power, this is also equal to e power minus at whole inverse, which is nothing but phi of minus t whole inverse, right? Phi of t1 plus t2, which is e power a t1 plus t2, which is nothing but e power a t1 times e power a t2, that is phi of t1 times phi of t2. And similarly, if I want to do phi of t2 minus t1 times phi of t1 minus t naught, which is nothing but phi of t2 minus t naught. These properties are very useful when we get into controller designs. Right? Now, let's look at very important concept on complete state controllability. Right? This state controllability and observability, stability concepts are very important to understand. Right? For what we are going to do is we are going to consider linear time invariant system, which is represented in the form of x dot is equal to ax of t, x dot of t, ax of t, bu of t. For ease, I am going to drop the term t. I am going to say x dot is equal to ax plus bu. That system is said to be controllable at time t naught if it is possible to find an unconstrained control vector. I am not putting any constraint on my input u of t to transfer the system from any initial state x of t naught to any final state x of tf in a finite interval. Right? What I meant is, if there exists a control input, there is with a unconstrained control input applied on the system, then I can take the system from any initial state x naught to a final state x of tf. Right? Then I can say that particular system is controllable. Okay? It's a very important property. How do I determine the controllability? I need to find the controllability matrix, which is C. Right? The controllability matrix is based on A and B of the system matrices B, AB, A power n minus 1 B. These are the columns of the C matrix, right? If all these vector B, AB, A power n minus 1 B are independent, linearly independent, then the system will be said to be controllable. Or what I can say is, if I find the rank of the C matrix, the rank is full, then I can say the system is completely state controllable. Means all the states are controllable, right? Complete state controllability tests require the matrix C to have a rank, full rank, right? Rank should be equal to n. Or I can say the vector B, AB, A power n minus 1 B are linearly independent. Okay. Now, what is the necessary and sufficient condition for a complete state controllability? Remember, there should not be any pole zero cancellation in the transfer function or the transfer matrix, right? If there is a pole zero cancellation occurs, the system cannot be controlled in the direction of the cancel mode, right? For example, if I take a system y of s by u of s, it has two poles, one at 2 and another one is s of s minus 1, right? The numerator has a 0. You see here there is this pole and 0 is getting cancelled. Eventually what you get is y of s by u of s is a first order system. There is a pole zero cancellation taking place. If there is a pole zero cancellation taking place, then the system cannot be controlled in that particular cancelled mode. This particular mode is not controllable at all, right? So one of the issues you have to take care of pole zero. Look at the pole zero cancellation. If it's you want to get a complete state controllability, I don't want any pole zero cancellation. Okay. Now let's look at another important concept called complete observability. Again, let's look at the definition of observability. If you take a linear time invariant system, right, LTI system, x dot equal to ax plus bu. I mentioned earlier, I am going to drop the term t for ease. Y is equal to cx plus du. That's a system. Observability, I am talking about what I can observe, right, is said to be observable at time t naught if the system state x of t naught, right, it is possible to determine the state, initial condition x of t naught, from the observation y of t over a finite time interval. When I have observation y of t over finite time interval, if I can determine the state x of t naught, then the system is said to be observable, right? How do I test this observability? Again, I will create observability matrix O. I will take the row C matrix C, CA, CA power n minus 1. Remember, C is a row vector, right? C could be a, if your outputs are m outputs are there, C could be m cross n, right? C times A is n cross n. C is m cross n times n cross n, you will get m cross n, right? CA, C, CA, CA power n minus 1. You create these rows. If all these are linearly independent, then your system is said to be completely observable, or I can say the observability matrix has a full rank, then I can say the system is completely observable. Okay. Now there are two other concepts is very important when we go into controller design using a modern control theory, right? Stabilizability, right? For a partially controllable system, if uncontrollable modes are stable and the unstable modes are controllable, then the system is stabilizable, right? That's something which we need to understand, right? What I meant is there are modes which is uncontrollable, right, but they are stable. there are unstable modes or controllable, then I can stabilize the system. Right? There is another thing, detectability. Again, for a partial observable system, if unobservable modes are stable, whereas the observable modes are unstable, the system is said to be detectable. Okay. Why controller canonical form is important? Why we focus only on controller canonical form, right? It simplifies the verification of the controllability, right? Controllability is an important test, right? What controllability says? All the states of the systems are controllable. Why do we need? We have to design a feedback control. The purpose of feedback control is to stabilize the system and also improve the robustness against the disturbances, right? If some of the states are not controllable, then if that particular state is unstable, then we can't do anything. Even if you do a feedback control, you cannot control that particular state. So controllability is a very important test. For controllability, if you don't represent the state, if you represent the states in a controller canonical form, right, then the controllability state will become very simple. It's also suitable for pole placement design, right, and for a full state feedback controller synthesis. See, what happens is whenever the system is given, we do the transition analysis to understand what are the specifications we are getting, right, for an open loop system. We try to understand what is the rise time, what is the settling time, whether the system is stable or not, right. Suppose you want to modify the transient characteristics, then you need to design a feedback controller. So you have to position your poles of this closed loop poles of the system such that the closed loop system satisfy your requirement, right. So when you want to go for pole placement design or a full state feedback controller, right, the controllability test is important. In such cases, if you represent the system in a controllable canonical form, it makes your life easier. Okay. It's also provide a systematic way to convert a transfer function to state space model, right. It's useful in controller design and its implementation, right. The controller canonical form has a dual, the observable canonical form, right. Understanding controller canonical form helps to build intuition over the observer design as well, right. Why Jordan canonical form is important? Jordan canonical form extends a diagonalization of matrices that are not diagonalizable, right. Represents any square matrix with the complex entries in near diagonal form using Jordan blocks, right. It simplifies the computation. If you want to compute e power at state transition matrix, and if you represent A in a Jordan form, right, and then what will happen is you will nicely get e power P1t, e power P2t, e power P3t. The P1, P2, P3 are your pole locations straight away. So if you convert any standard form into Jordan form, and from Jordan form one can easily compute state transition matrix. Okay. It supports design and analysis of uncontrollable or unobservable systems, right. In a summary, this particular course, this particular lecture introduces the concept of different forms of representation, right. From a transfer function, one can represent the system in a controller canonical form or Jordan canonical form, right. And you also see that state space representation is not unique. You can represent the system in multiple forms, right. And we also talked about a state transition matrix, how state transition matrix, what are the properties of state transition matrix, what are the significance of it. We also talked about two important concepts, controllability and observability of the system. And we also saw how to test the controllability of the system and observability of the system, right? This controllability and why we need controller canonical form, Jordan canonical form, what are the significance of it, right? And this gives you an idea. If a system transfer function is given, you can represent them in one specific form, and you can use them for your controller design, right? You'll be able to appreciate the usefulness of controllable canonical form and Jordan canonical form when we go into pole placement design. So some reading material, right? Modern Control Engineering by Ogata is a very good book. You can just look into the state space form, different canonical form and controllability and observability, right? Or you can also look at Modern Control System by Richard or Control System Engineering by Norman. These are very good book which will help you to understand canonical forms, and it gives a lot of examples. In this course, we are just talking only about multi-rotor case. They are provided for different mechanical, electrical subsystems, and that will useful for you to understand this concept very well. Thank you.